Welcome, my dear students. So, in the previous lectures, we have discussed about normed spaces, especially complete normed spaces. Okay, and complete normed spaces, you have to prove two distinct property. One is completeness. Okay, so for all the spaces which we have discussed, the completeness property was established in section 1.6 using metric. Okay, and second thing is we have to prove that the space is normed. So for that you have to use four conditions: n1, condition n2, condition n3, and n4. The first two conditions are essentially same as, and the fourth conditions are essentially same as in the case of metric. Third condition is, in all the cases, all the examples which I gave you, third condition is very easy to compute. So that's why I gave you that condition. Next is so we have established that there are normed spaces which are actually complete. Now, third, there are spaces in which the space is not complete or incomplete normed spaces. Okay. So I'll give you one or two examples of incomplete normed spaces. First example is set of all rational numbers Q. Here, norm x is defined as mod x. In R also, we can define a norm by norm x is equal to mod x, which is complete, since R is complete. But in the case of Q, if you define a norm by norm x is equal to mod x, the space is not complete, because you can always take an arbitrary sequence. I think I gave you an example of a sequence in which this does not hold. One of the classic examples is a sequence xn, which is defined as, if you take the value of root 2, okay, so root 2 is 1.4, 1.41, 1.414, etc. So in this sequence, you are at each term you are adding a digit of root 2. That's the only thing. Okay, we already know that the digit root 2, the number root 2 has infinitely many digits. So you are essentially adding every term a new digit of root 2 onto the mix. That's what this sequence is. So clearly this sequence is emerged from root 2, so this sequence converges to root 2. Here 1.4 is rational, 1.41 is rational, 1.414 is rational, etc. All these are rational numbers. Clearly, this is actually a real sequence. In a real sequence, every convergent sequence is Cauchy. This is a Cauchy sequence as well. In rational as well, this is a Cauchy sequence. Okay, so if you want, you can prove that modulus of xm minus xn is very less compared to any number, which is less than 10 raised to minus n or something like that. So you can easily prove that this is a Cauchy sequence which converges to root 2. This is a sequence of rational numbers which converges to actually root 2. So clearly we can say that this is a Cauchy sequence which converges to an irrational number, or which does not converges in Q, because root 2 is an irrational number. Root 2 does not belong to Q. So we have a Cauchy sequence xn which does not converge in Q. So in order for a space to be complete, every Cauchy sequence must converge in the space itself. Here we have a sequence which converges, but it does not converge in Q. So the space Q is not complete. So earlier I gave you another sequence yn is defined as box of 2 raised to nx by 2 raised to n. Box x is the greatest integer function. Okay, if x is an irrational number, okay, Clearly, box of 2 raised to nx is numerator is integer, denominator is power of 2, which is an integer, so which is of the form some p by q, which belongs to q. So yn is a rational sequence. Okay. In fact, we have already established that yn converges to x. We have already established this fact. Okay. So you can easily use other techniques to establish the same fact as well. So this sequence converges to x. Since x is chosen to be an irrational number, this is a Cauchy sequence. Yn is Cauchy, but yn does not converge in Q. Okay, so there are other Cauchy sequences. In fact, there are infinitely many Cauchy sequences in Q which does not converge in Q itself. So this space Q with the norm x is equal to modulus of x is not at all complete. Okay, so we can easily understand that. Another example of an incomplete space is something which we have already discussed about. Okay, the space of all polynomials. If you take the space of all polynomials, space of all polynomials on closed interval AB, which is an example which we have defined on section 1.6, I guess. We already discussed that the space is not complete, so I have chosen you some examples as well. So if you define here norm x is equal to maximum of the element of J closed interval AB modulus of x of t. If you define that, then you can clearly understand that this space is not complete. You can take a Cauchy sequence as, I guess, xn is equal to, I guess, summation n is equal to j is equal to, j is equal to 0 to n, x raised to n by n factorial. Okay, x raised to j, x raised to j by j factorial. Here j is the variable. Okay, so this is actually 1 plus x by 1 factorial plus x square by 2 factorial plus etc. plus x raised to n by n factorial. This contains exactly n plus 1 times. Clearly, this is a polynomial of degree n. Okay, so xn is a polynomial of degree n. Okay, so this belongs to, if you define x to be in closed interval AB, this is a polynomial of degree n which belongs to this space. If we can denote this space as capital X, so this xn belongs to X. So this is a space which is defined on the space of all polynomials. So if we take limit n tends to infinity xn, which is limit j n tends to infinity summation j is equal to 0 to n x raised to j by j factorial, which is actually summation j is equal to 0 to infinity x raised to j by j factorial. This is what we get. So we already know that this sequence, this value is actually is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. This is keep going on, which is actually e raised to x, which is not a polynomial. So actually we have taken where x is an element in closed interval AB. So actually we have taken a polynomial sequence 1 plus x by 1 factorial, x square by 2 factorial, etc. x raised to n by n factorial, which is a Cauchy sequence. Okay, then if we take the limit of that sequence, we get a series of this form, which is actually the series of e raised to x. So we have taken a polynomial sequence, polynomial Cauchy sequence, which converges to what? E raised to x. Okay, but this is not a polynomial, which implies this is not an element of capital X. So we have a polynomial sequence which is Cauchy, which is not converge in capital X. So the space of all polynomials on closed interval AB is also not complete. Okay, you can use several other arguments for the same sake as well. Okay, so another argument is, I think it's an interesting argument, which says that you have a theorem which is called Weierstrass approximation theorem. Okay, that theorem says that every continuous function on some interval, closed interval AB, can be approximated using a polynomial. So if we take a continuous function C, you always get a sequence xn. This sequence is polynomials such that this sequence xn approaches to C. So this is true for every continuous function C defined on closed interval AB. So this is what Weierstrass approximation theorem. So if we take the polynomials xn to be in closed interval AB, so polynomials are always continuous function. So a continuous function can be approximated using polynomials. So these are polynomials xn. Now look onto xn. So xn's are polynomials. Okay, which converges to C. C is just a continuous function. We know that in general, every continuous function need not be a polynomial. So you have several examples for that. Sin x is an example, cos x is an example, e raised to x is an example, log x is an example. These are all functions which are continuous but not polynomials. Okay, continuous wherever it is different. So using Weierstrass approximation theorem, every continuous function can be approximated using polynomials, which means that there exist polynomials which converges to a continuous function. But in general, a continuous function need not become a polynomial. So consider for sin x. There exists a sequence xn of polynomials which converges to sin x. This xn belongs to our space x of all polynomials in closed interval AB, but its limit function sin x is not element of x. Similarly, if we take a yn of polynomials in capital X, which converges to cos x, but cos x is not a polynomial. So, from this argument itself, using Weierstrass approximation theorem, we can clearly state that there exists Cauchy polynomial sequence which does not converge to polynomial in general. So this is also an example of an incomplete space, Normed space. Okay. Here also keep in mind that we have used the same arguments as in the case of metric, because every norm induces a metric. Okay, that's the reason we use the same argument as in the metric. D of xy can be written as norm of x minus y. So every norm induces a metric. So our properties of completeness in the case of norm should be similar to the properties of completeness with respect to the corresponding metric. So that's why we proved the completeness of or incompleteness of the normed space with respect to the completeness and incompleteness of the metric. I hope you understood.